The vastness of oceans and their creatures. Chapter 1. Introduction: Why Oceans Matter. Learning Objectives. By the end of this chapter, you should be able to 1. Explain why oceans are central to Earth's climate, chemistry, and biology. 2. Describe how the ocean supports human life, economies, and cultures. 3. Identify major ways scientists study the ocean and why so much remains unexplored. 4. Summarize the key challenges facing the ocean in the 21st century. 1.1 The Ocean Planet. Look at a photograph of Earth from space and you immediately see why our home is called the Blue Planet. Oceans cover about 71% of Earth's surface, over 361 million square kilometers, and store roughly 97% of Earth's water. The average ocean depth is around 3.7 kilometers, with trenches plunging to nearly 11 kilometers, deeper than Mount Everest is tall. This immense connected body of water forms a single global ocean with 5 named basins: Pacific, Atlantic, Indian, Southern, and Arctic, linked by powerful currents that move heat, salt, nutrients, and life around the planet. These basic facts are more than trivia. They tell us that to understand Earth, you must understand the ocean. It moderates climate, sculpts weather, feeds billions, supports economies, and harbors the vast majority of Earth's living space by volume. Yet over 80% of the seafloor remains unmapped and unexplored at high resolution, and new species are discovered every year, especially in deep, dark habitats that humans rarely see. 1 point to the ocean climate engine. The ocean is Earth's largest heat reservoir. Sunlight warms tropical surface waters, and winds plus differences in water density controlled by temperature and salinity drive a global conveyor belt circulation that redistributes heat. This circulation, sometimes called the thermaline circulation, helps keep Europe warmer than its latitude would suggest and influences monsoons, hurricane tracks, and drought cycles. To major players shape this engine, surface currents driven mainly by winds, for example, the Gulf Stream, Kuroshio move warm water poleward and cool water equatorward. Deep circulation, where dense waters sink near the poles and slowly creep along the abyss before upwelling elsewhere, returns nutrients to sunlit layers and sequesters carbon for decades to millennia. In parallel, the ocean exchanges gases with the atmosphere. Microscopic marine plants called phytoplankton photosynthesize, drawing in carbon dioxide, CO, and releasing oxygen. Over geological time scales, the ocean has absorbed a significant fraction of humanity's CO emissions, buffering surface warming but leading to ocean acidification, a subtle shift in seawater chemistry that challenges shell-forming organisms. Key takeaway: if you care about weather where you live tomorrow and climate everywhere for centuries, you care about the ocean today.
1.3 The ocean as the lungs and larder of the planet's oxygen production. Marine photosynthesizers, mainly phytoplankton and cyanobacteria, contribute a large share of the world's oxygen production. Much of this oxygen is consumed within the ocean itself through respiration and decomposition, but the net effect over time has helped maintain breathable air. Food and nutrition. Oceans provide protein for billions of people. Wild fisheries, aquaculture, fish farms, and seaweeds supply essential nutrients and livelihoods, especially in coastal nations. Species range from small pelagics like sardines and anchovies to high-value tuna and demersal fish, plus shellfish, cephalopods, and crustaceans. Healthy marine ecosystems underpin this food web. Plankton feeds small fish feed larger fish, seabirds, and marine mammals. Apex predators help keep populations balanced. Medicines and materials. The chemical ingenuity of marine organisms, sponges, tunicates, algae, bacteria has yielded compounds investigated for pain relief, antiviral therapies, and cancer drugs. Bioprospecting must be done ethically and sustainably, but the ocean's molecular diversity remains a largely untapped library. 1 point for the ocean economy and human well-being. Shipping and trade. About 80 to 90% of global trade by volume moves by sea. Ports, shipping lanes, and choke points like the Strait of Malacca or the Suez Canal are critical to supply chains and national security. Maritime industries from shipbuilding to logistics employ millions. Energy, offshore oil and gas have long histories, but the fastest-growing sector is renewable offshore wind, wave, tidal, and the promise of floating solar. These can decarbonize grids, especially for coastal cities. Tourism and recreation. Coasts and islands attract visitors for beaches, diving, surfing, wildlife viewing, and cultural heritage. Tourism can bring income and conservation incentives, but poorly managed development can erode habitats and exclude local communities. Coastal protection and blue infrastructure. Natural systems such as mangroves, coral reefs, and salt marshes buffer storm surges and reduce erosion. Investing in these green protections often costs less and delivers more co-benefits than concrete seawalls alone. Cultural and spiritual values. From Pacific voyaging to indigenous coastal stewardship, from maritime music to sacred seascapes, the ocean shapes identities and languages. Recognizing these values helps design conservation that is fair and effective. 1.5 A living mosaic. Biodiversity from surface to seafloor. The ocean holds staggering biodiversity, not just many species, but many ways of life. Sunlit surface waters teem with planktonic drifters and fast-swimming predators. Coral reefs host kaleidoscopic fish and invertebrates. Kelp forests sway with sea otters and urchins. In the deep sea, where light never penetrates, organisms glow with bioluminescence, feed on falling marine snow.
Vertical and horizontal gradients organize this life. Light and depth photosynthesis occurs in the upper euphotic zone, roughly the top 200 meters. Below that, the twilight zone mesopelagic hosts the largest migration on Earth as billions of organisms rise at night to feed and sink by day to avoid predators. Temperature and nutrients. Cold, nutrient-rich upwelling zones fuel plankton blooms and rich fisheries, for example, off Peru. Namibia, while warm, nutrient-poor gyres are biological deserts by comparison. Habitats. From seagrass meadows to abyssal plains, each habitat offers different niches, shaping evolution and behavior. Biodiversity supports resilience. Diverse ecosystems are generally better at withstanding shocks and maintaining functions like carbon storage and food production. 1.6 Hazards and risks from the sea. The ocean inspires awe, but it also demands respect. Storms and flooding. Tropical cyclones and storm surges can devastate coasts. Warming seas provide more energy to storms, and rising sea levels worsen flooding. Tsunamis, undersea earthquakes, landslides, or volcanic eruptions can send destructive waves across basins in hours. Harmful algal blooms HABs. Under certain conditions, microalgae bloom and release toxins, closing fisheries and threatening health. Erosion and saltwater intrusion. Shorelines shift naturally, but human development can amplify loss of land and contaminate freshwater. Risk is a combination of hazard, exposure, and vulnerability. Building wisely, restoring natural buffers, and improving early warning systems reduce disaster impacts. 1.7 How we know what we know. Marine science blends ships, satellites, autonomous robots, and mathematics. Satellites map sea surface temperature, color a proxy for plankton, height, and wind, giving a global, near real-time view. Argo floats drift and dive through the upper 2,000 meters, profiling temperature and salinity. Newer deep Argo floats reach the abyss. Biogeochemical floats add oxygen, pH, nitrate, and more. Gliders and AUVs autonomous underwater vehicles patrol coasts and the open ocean for weeks, sampling where ships can't. Moored buoys and coastal stations provide long-term records. Ships remain vital for collecting water, sediments, and specimens. Acoustics. From passive listening to active sonar reveals animal movements, seafloor shapes, and internal waves. Despite these tools, the ocean's vastness and harsh conditions keep many regions undersampled. Better coverage and open data help scientists detect change and improve forecasts. 1.8 The 21st Century Ocean. Challenges at a glance. For intertwined pressures dominate the modern ocean story. 1. Warming, extra heat in the climate system is mostly absorbed by the ocean, raising temperatures, altering currents, and intensifying marine heat waves that bleach corals and stress wildlife. 2. Acidification. As CO dissolves into seawater, it forms carbonic acid, lowering pH and reducing carbonate availability, troubling for corals, oysters, and plankton that build calcium carbonate skeletons. 3. Deoxygenation. Warmer water holds less oxygen. Stratification limits mixing. Expanding oxygen minimum zones challenge fish and invertebrates and can shift food webs. For dot pollution and overuse, plastics, nutrients, oil, noise, and chemical contaminants stress ecosystems. Overfishing, destructive gear, and habitat loss undermine resilience. These pressures interact. For example, nutrient pollution can trigger algal blooms. When the algae die, decomposition strips oxygen from the water, creating dead zones. Effective solutions, therefore, address multiple stressors together. 1.9 Blue Solutions, Hope in Action. Despite sobering trends, solutions are real and growing. Marine Protected Areas (MPAs). Well-designed and well-enforced MPAs allow ecosystems to recover, increasing biomass and spillover benefits to nearby fisheries. Sustainable fisheries, science-based catch limits, bycatch reduction, rights-based management, and traceability can rebuild stocks and support communities. Coastal habitat restoration, replanting mangroves, restoring reefs and marshes, and reconnecting rivers to estuaries protect coasts and store carbon. Blue carbon. Clean energy and transport, electrifying ports, decarbonizing shipping fuels, and scaling offshore renewables cut greenhouse gases and air pollution. Waste and pollution controls, reducing plastic at the source, improving wastewater treatment, and eliminating toxic discharges relieve chronic pressures. 1.10 A day in the life of the ocean. Every day, tides rise and fall under the pull of the moon and sun. Winds stir the surface, mixing oxygen downward. In the open sea, countless creatures perform the diel vertical migration, a nightly ascent of the world's largest animal movement to feed on surface plankton under the cover of darkness. Along coasts, kelp canopies surge with waves, seagrasses exhale oxygen bubbles, and coral polyps extend tentacles to capture passing food. Even far offshore, marine snowflakes of organic debris drifts continuously into the deep, fueling life in perpetual night. This rhythmic pulse connects surface and depths, coast and open ocean, physics and biology. Understanding these connections is central to managing the ocean wisely. 1.11 Key terms: euphotic zone, sunlit surface layer where photosynthesis occurs. Thermaline circulation, global movement of seawater driven by temperature and salinity differences. Upwelling, wind-driven rise of deep, cold, nutrient-rich water to the surface. Ocean acidification, decrease in ocean pH due to absorption of atmospheric CO. Blue carbon, carbon stored in coastal and marine ecosystems, mangroves, marshes, seagrasses. Marine heat wave, prolonged period of unusually warm ocean temperatures in a region.